Welcome. In this video, we will solve the boundary value problem step by step to find its eigenvalues and eigenfunctions. We are given the second order differential equation y double prime plus lambda y equals 0. This is subject to the boundary conditions y of 0 equals 0 and y of pi equals 0. To solve this, we must check three cases for lambda. Lambda equals 0, lambda is negative, and lambda is positive. Let's start with case 1, where lambda equals 0. The differential equation simplifies to y double prime equals 0. Integrating to y's with respect to x gives the general solution y of x equals a x plus b. Applying the first boundary condition y of 0 equals 0, we find that b must be 0. Applying the second boundary condition y of pi equals 0 implies that a times pi equals 0. So a is also 0. Since both constants are 0, we only get the trivial solution. Therefore, 0 is not an eigenvalue. Now for case 2, assume lambda is negative. Let lambda equal negative k squared, where k is positive. The general solution involves hyperbolic functions c1 cos kx plus c2 sin kx. Using the first condition, y of 0 equals 0. Since cos of 0 is 1 and sin of 0 is 0, c1 must be 0. Using the second condition, y pi equals 0 leaves us with c 2 times sin of k pi equals 0. Since k is strictly positive, the hyperbolic function is never 0. Thus, c2 must be 0. Again, we get a trivial solution, meaning no negative eigenvalues exist. Finally, let's look at case 3, where lambda is positive. Let lambda equal k squared. The roots of the characteristic equation are imaginary, giving a general solution of c1 cosine kx plus c2 sin kx. Applying y of 0 equals 0 forces c1 to be 0. Since sine cosine of 0 is 1, applying y of pi equals 0 gives c. 2 times sine of k pi equals 0. To avoid the trivial solution, c2 must not be 0. Therefore, sine of k pi must be exactly 0. The sine function is 0 at integer multiples of pi, which means k pi equals n pi. Simplifying to k equals n. In conclusion, substituting k equals n back into our definition of lambda gives our eigenvalues lambda sub n equals n squared. And our corresponding non-trivial solution, the eigenfunctions are y sub n of x equals sine of nx. This perfectly solved the boundary value problem. Thanks for watching.